Okay, so we are back again, right. In the previous lecture, we started with this example. This your what you call this is a 5 bus problem, and this xd1 dash for this generator, and one transformer is there here and here, right. Two transformers are there. So, previous examples we have not considered the transformers. If transformers are there, then the transformer reactance will be given in per unit, along with that this one you add, right. So, we did not make any bus number here, actually there is no need, right. So, basically it is a 5 bus problem, and another thing is for this problem that bus 2 and bus 3 basically they are PV bus, whatever it is given that is their load flow solution, these two are PV bus. That means, its voltage magnitude is 1.03 per unit is defined, right. Similarly, for bus 3 that V 3 is equal to 1.02 per unit, its magnitude is defined, right. So, whatever angles you are it is given here, this is a load flow solution from the load flow solution, right. So, all I mean load flow solutions everything is shown here, right. V 5, then your what you call V 4, right, everything is shown here. And another point is that your all the load impedances are load power is given, we have to convert it to admittances, right. So, load power is given, and at the same time you have to compute E1 and E2, right, and this is infinite your what this is a slack bus, and this is actually shown by your what you call infinite bus, right. So, in this case E1 is equal to V1 is equal to 1 angle 0, just to your what you call to simplify the problem, because we have to do something which can be solvable in the class, and in this case that your R x in per unit for all the 3 lines are given, right, but for the classroom exercise if we take R it will consume more time. So, we will restrict it to your what you call the reactances, but for this example this R and X will be there, right. So, E1 tilde that is phasor quantity is equal to E1 angle delta 1 and E2 tilde is equal to E2 angle delta 2. So, half line charging other data are also there, right. So, just hold on. So, if we come back to the other data, just let me make it this thing. So, half line charging, that all the line charging is given. So, B 4 5 by 2 that is your charging susceptance, right. It is given J 0.113 and B 5 I mean half B 5 1 it is J 0.098 and half B 4 1 it is J 0.041, because half will take, right. And then H 1 is 12 second and H 2 is 9 second, the inertia of the two machines, right, 1 and 2. And transformer for X T 1 that is nothing but X 2 4 it is J 0.022, that is this one that is X 2 4 that is nothing but X T 1. Similarly, for T 2 transformer T 2 it is X 3 5, right. So, these two are given X T 1 is equal to X 2 your X 2 4 and X T 2 is equal to X 3 5, that is J 0.0, all are in per unit, right. So, buses 2 and 3 are PV buses, right, and PG 2 is given 3.25, PG 3 given 2.10, and as 2 and 3 are PV buses, after solving this, right, that QG 2 is 0.6986 and QG 3 0.3110, right. Now, load flow solution. So, these are the load flow solution for the pre-fault condition. I mean you have to run the load flow and get, but for the assignment or exam purpose this solution will be given, because we know that exam it is not possible to simulate or this that, right. So, this solution will be provided to you. So, V 1 is equal to 1 angle 0 the slack bus, V 2 is 1.03 angle 8.35 degree, this bus 2 I told you is a PV bus. So, voltage magnitudes are specified. Similarly, bus 3 also is a PV bus. So, it is 1.02 angle 7.17 degree PU, that is PV bus, and V 4 and V 5 that is 1.0174 angle 4.32, 4 and 5 are PQ buses, and V 5 1.0112 angle 2.69 degree, right. These are the load flow solutions. Now, this is given, from that we have to find out that before determining your swing equation, we have to find out the swing equations for those two machines. So, we have to obtain E1, E2 and E3, right. So, we know that that current I 2 will be P 2 minus j q 2 upon V 2 conjugate, right. Because we have to find out E 1 E 2 sorry E 2 and E 3, because E 1 is equal to V 1 is known, that is 1 angle 0, right, and therefore, P 2 and Q 2 your all are given. So, all you have got from your load flow solution. So, you can find out what is the current I 2 in the current injection, that is your at bus 2, that your current injection, right, I 2. So, it is P 2 at the from load flow studies, you have got 3.25 minus j 0.6986 upon 1.03 angle minus 8.35 degree, right. So, multiply both sides by x d 1 dash I 2, because if you go back to the diagram, right, we have to complete this is actually bus 2 and this is your x d 1 dash, right. So, we have to use that equation 9, that is why we are multiplying by x d 1 dash for by I 2, right. So, here your x d 1 I 2 x d 1 dash I 2. So, if you multiply by x d 1 dash I 2, it will be like this, and if you simplify all these things, you will get your E 2 is equal to that voltage is known 1.03 angle 8.35 degree, that is your this voltage your just hold on, this voltage, that is your V 2, right, just hold on, this is your V 2. If you come back to this diagram, this E 1 tilde, I mean this one you see that if you come back to this portion, right. So, E 1 angle delta 1, right, is equal to your this current injection here is I 2. So, your I 2 into x d I 2 into x d 1 dash plus this V 2, right, V 2 is equal to 1.03 angle 8.235 degree. Similarly, if you come to this one, actually here also it will be E 2 angle delta 2 is equal to that voltage V 3, this one, plus here that current injection is I 3 into x d 2 dash, because this is bus 3, right. So, that same philosophy is applied here for computing that. So, here you will get, if you simplify this one, you will get E 2 is equal to this much, right. So, it will come 1.096.3377, it is actually in radian, not in degree, I have written delta 2 in radian, right. Note that your E 1 is equal to 1 angle 0 degree, because bus 1 is a slack bus and it is shown infinite bus, no x d 1, x d 2 or no x d 1 dash there. So, it is E 1 is equal to simply 1 angle 0 degree, right, or radian, whatever it is. Similarly, for I 3 if you calculate, it will be P 3 minus j q 3 upon V 3 conjugate, right. So, it is 2.1. So, minus j 0.311. So, it is 1.02 angle minus 7.16 degree, that is your I 3, right. So, here also I repeat that E 1 is 1 angle 0, because bus 1 is a slack bus, right. And similarly, you multiply x d 3 dash your I 3, right. So, if you come back to this bus 3, right, bus 3, same thing here, that your this one will be make x d 3, just this bus 3. So, that is why make it x d 3, not x d 2, right. So, that symmetry, or what you call this with bus number, this x d 3 dash, this number 3 will be maintained, right. So, it by mistake I have made an x d 2, you make x d 3 dash, right. So, otherwise you can keep x 2 also, does not matter, only calculation should be correct. So, this one when you do that, your E 3 that E 3 is equal to your V 3 plus x d 3 I 3. In general, if we put like this, right. So, basically it will be your what you call that your whatever it comes, say E 3 tilde, I can put like this E 3 tilde, it is basically it is a phasor quantity. So, it is 1.071 after simplifying this angle 0.3184 radian, because delta 3 we have given it as a radian. So, this E 1, E 2 and E 3 easily you can compute if you know the current injection, if you know other parameters, and of course, that pre-fault case the load flow solution must be known to you, then only you can compute all this, right. So, the the loads at buses 4 and 5 are represented by the admittances calculated as follows. This one we have your what you call, we have seen it before, that at bus 4 the load is given 1 minus j 0.44 divided by the magnitude of your V4 square. This already we have seen for the previous example, and this is your load. If you simplify, that load admittance will become 0.9661 minus j 0.4251, right. Similarly, for bus 5 load is given 0.5 minus j 0.16 divided by this V5 square, V5 magnitude, so 1.0112 square, right. If you do so, it will be 0.4889 minus j 0.1564. So, these two load admittances are known. Now, you have to compute the YOS matrix for pre fault, fault and post fault condition, right. So, now pre fault bus matrix, right. So, load admittances along with the transient reactances are used with the tie line and transformer admittances to form the pre fault augmented bus admittance matrix, right, which contains the transient reactances of the machine. We will therefore now designate as bus 2 and 3 the fixed TCS. That is why 1 and 2, that internal machine things we have not considered, club we are actually making it together. So, we will therefore now designate as bus 2 and 3 the fictitious internal nodes between the internal voltages and the transient reactances of the machine, right. This we will do. That means if we go back to the diagram, right, here, if you go back to the diagram, that Y22, the transformer is actually J 0.022, right, per unit. So, all these two things will be added together, right. So, you add 2 and take the reciprocal of that, then you will get your Y22, right. So, same philosophy will be here also, that whatever T2 reactance is there, transformer T2, we will add this one and we will take the reciprocal of that, such that we will get say Y33, right. So, we will come back to this thing, right. So, therefore, Y22 will be 1 upon your 0 j 0.067 plus the transformer 1, it is coming actually minus j 11.236, right, and Y24 will be Y42, it will be plus j 11.236. We know that we calculate small y11, small y12 like this, and capital 1 whatever it is I j is equal to your minus small y I j, this we know, right, and in diagonal one we just add all the small ones. So, diagonal will be always with a negative sign, right, and your off diagonal one will be minus of small y is minus. So, it will be positive sign, right. So, Y24 is equal to Y42, you will get J 11.236. Similarly, Y33 will come, that your this is your J 0.04, that is a transformer thing, plus that your that XD 3 dash, right. So, it is coming minus J 7.143. So, Y35 is equal to Y53 will be J 7.143, right. This you know from the load flow studies, how to construct that admittance matrix. So, now when we calculate Y44, all should be added, right. So, this is that load admittance, then Y41, small Y41, small Y45, then half B41, half B4 5 by 2, then plus small Y24. If you do so, so it will be your, this is your YL4, it is marked here, this is Y41, this is Y45, and this is half B41. Other things just let me move little bit up, right, and this is your half B45, that is J 0.113, and this is your minus J 11.2359, that small y24, right. So, if you whatever it comes, if you add together, you will get y44 will be 6.6598 minus j for 44.617, right. Similarly, y55 you calculate, you know how to. Only thing is that your load admittance, that is we will take as a shunt admittance, right, that has to be added. That is why it is YL5, it is there, we have already computed. If you add all, you will get y55 will be your 8.9769 minus j 57.2972. This is y55, right. And augmented pre-fault bus admittance matrix, right, that is that is your it is a 5 into 5 matrix. So, this is your, just hold on, let me reduce the size, right. So, this is your bus admittance matrix. So, it is a 5 into 5 matrix, right, and there all elements are shown, right. This is your pre-fault admittance matrix, right. Next is that bus matrix during fault, right. Since the fault is near bus 4, so it must be sorry, it must be short circuited to ground, right. It is a 3-phase fault. The y bus during the fault condition would therefore be obtained by deleting the 4th row and 4th column from the above augmented pre-fault y bus matrix. So, bus has occurred, that the 3-phase fault has occurred at bus 4. So, what you will do is that 3-phase fault. So, this row should be eliminated and this column should be eliminated, right. So, finally, it will come down to a your what you call 4 into 4 matrix. So, this element will be retained, right. This one and this one will be retained, this one will be retained, and this one and this one will be retained. So, this will go, all will be 0 0 0, all will be 0 0 0 during fault, right. That means, in general, if you want to make, say we want to make it as 5 into 5, then in that case this will be 0, this will be 0 0 0, this will be 0 0 and 0, right. So, all these things you have to what you call 4th row and 4th column you have to eliminate. So, if we do so, then the reduced fault matrix, that during fault, right. So, it will be, it actually what happened, that it is a reduced fault matrix. Reduced fault matrix means that just I am making it here, because all these calculations are not shown, then it will be too lengthy, right. So, only thing is that you will make this will eliminate, right. So, this will not be there. So, ultimately it will be a 4 into 4 matrix, right. It will be a 4 into 4 matrix, right, but you have 3 machines, right. So, in that case you what you will do, so this will be a 4 into 4 matrix. So, YNN, right, it will be actually y 3 into 3, right, YNN, YNR, YRN, YRR, right. After that same philosophy, that to the y matrix reduction, that has been done. So, that is why this your what you call that y reduced matrix will be 3 into 3 during fault, because 3 machines were there. So, we have reduced this one to your 3 into 3. Actually, during fault it is 4 into 4, right, but YNN, n is 3, because number of machine is 3. So, it is 3 into 3 YNN, then NR, R is 1, right. So, that your 3 into 1, then 1 into 3, then YRR, right, only one element. So, after that you reduce it, that using that formula YNN minus your what you call YNR, then YRR inverse into your what you call RN, right. So, after reducing this, we are getting this one, but it has to be a symmetric, your say what you call symmetric matrix. It is a symmetric matrix, right. So, it is a symmetric matrix, that 1 3 3 1, 1 2 2 1, and your 1 2 3 1 3 2, right. It is a symmetric matrix. If you do not get symmetric matrix, then somewhere something has gone wrong in the calculation, right. So, this is actually reduced fault matrix, that is 3 into 3. Now, when fault was cleared, that line 4 and 5, that your what you call that post fault bus matrix, that is removed. Now, once the fault is cleared, by removing the line, simultaneously opening the circuit breakers at the either ends of the line between buses 4 and 5. That means you have to reconstruct the Y matrix. So, if 4 5 is open then Y 4 5 will be Y 5 4 will be is equal to 0, and accordingly you have to modify the Y bus matrix, right. So, that means that you are subtracting the series admittance of line 4 5 and the capacitive susceptance half of the line from elements Y 4 4 and Y 5 5. So, this will be changed. First thing is Y 4 5 is equal to Y 5 4 will be 0, and second thing diagonal element Y 4 4 and Y 5 5 you have to change. So, that is Y 4 4 post fault will be Y 4 4 pre fault minus Y 4 5 minus B 4 5 by 2. Whatever it comes, that is actually 5.2111 minus J 35.8771, right. Similarly, that Y 5 5 post fault you will get 7.5281 minus J 48.5563, right. Now, the reduced your what you call post fault bus is shown in the given thing. Actually, this matrix actually that post fault matrix actually your 5 into 5 matrix, right. After that you are reducing this. So, in that case same philosophy you follow, that YNN, that is 3 into 3 matrix, you just partition and then you reduce it to your 3 into 3 matrix. All these things are not shown because it is little bit lengthy, right. Only I have shown the reduced Y bus for the 3 into 3 one. It is 5 into 5, then you make it 3 your YNN 3 into 3, YNR 3 into 2, then 2 into 3, and that was YRR, it is 2 into 2, right. So, accordingly you just your what you call, you just calculate and and you will get this one, right. So, this is your reduced matrix. So, if you look here also, that this one and this one Y 1 2 Y 2 1, it is a symmetric matrix, then Y 1 3 Y 3 1 and Y 2 3 and Y 3 2, they are all same, right. So, it is actually 3 into 3 that reduced matrix, because you have a number of machines. So, accordingly you can reduce this one, right. This already we have seen before. After this note that 0 element appears in second and third rows, right. This shows that physically the generators 1 and 2 are not your interconnected when line 4 and 5 is removed. So, if you look into that, the 0 element appears in second and third rows, right. If you look into that, this your Y 2 3 and Y 3 2 both are 0, right. So, that means the generators 1 and 2 are not interconnected when 4 and 5 is removed, right. So, from that it is some kind of physical interpretation looking at this matrix, right. So, now during fault the power angle equation. So, fault has your what you call P 2 will be is equal to 0, right, during fault, right, because if you go back to this diagram, if we go back to this diagram, right, just hold on here, because fault has occurred at bus 4, right, and this is your generator 1, right. So, basically P 2 will be equal to 0, right. So, just hold on. Let me go down. Here, right. So, during just amplify this one. So, P 2 is equal to your 0, right, and P 3, that real of Y 3 3, then your E 3 tilde E 3 conjugate plus E 3 tilde, then Y 3 1 tilde E 1 tilde, I mean all are complex quantity, and Y 3 2 is equal to 0. So, you can real part of this one will be basically P E 3. So, you know all this from your load flow studies, right. So, you can easily compute. So, basically it will be E 3 square G 3 3, because real part we are writing, plus E 1 E 3 Y 3 1, then cosine delta 3 1 minus theta 3 1, right. Therefore, P 3 is equal to all this value you substitute E 3 1.071 square into G 3 3 0.1362 plus your 1 into 1.071, because E1 is 1, E3 is this much, right, and then cosine of delta 3 minus the theta 31 will be 97 point your what you call 90.755 degree, that is the angle of Y31, right. So, that is theta 31. So, if that means PE3 is 0.1561 plus 5.531 sin delta 3 minus 0.755 degree, right. So, now post fault power angle equation. So, post fault case directly you can write when fault is cleared, right. So, that is your that you have to use that last matrix 3 into 3, right. So, P2 E2 square G22 plus E1 E2 Y21 cosine delta 21 minus theta 21. So, from that you substitute E2 is 1.096 square plus into 0.5005 plus 1 into 1.096 into 7.6321 into cosine delta 2 minus 91.662 degree, right. So, if you come back to this, right, if you come back to your this one, right. So, whenever you will I mean computing this one, you please take those your what you call take these values, I mean this G values and your B values, right, whatever it comes. So, in this case your this one it is 7.6321, right, whatever it is Y21 into your cosine delta 2 minus 91.662 degree, that is angle of Y21. So, you will get P2 is equal to 0.6012 plus 8.365 sin delta 2 minus 1.662, right. Similarly, when you will make it this one P3, when you will make it is E3 square G33 plus E1 E3 Y31, that is your then cosine delta 31 minus your theta 31, right. So, in this case you substitute all these values, right. So, you will get your what you call that 0.1823 plus 6.5282 sin delta 3 minus 0.8466. Now, in this case your what you call that your Y31 and your Y21 or Y12, right. So, Y31 when you will go to this Y31 and Y12, you will only take the magnitude of this one, because it is magnitude of Y, right. So, when you do this, that you will get this P3 equation like this, right. So, P2 P3 equations we have got your post fault condition. Now, swing equation during fault. So, we know that d square delta upon dt square 180f upon H2 PM2 minus P2 is equal to P2 is 0 during fault, right, P2 is 0. So, it will be 180f upon H2, we are writing PA2, the accelerating power, right. So, d square delta upon dt square basically 180f upon 12, and it is basically 3.25. You go back to that your PG2, right. And similarly, your d square delta 3 upon dt square, it is 180f upon H3 PM3 minus P3, H1 was 2, H2 was 12, right. And similarly, H3 was 9. So, 180f upon PM and PM3 is 2.1, right, because we are assuming that it is a lossless turbine, right. So, 2.1 and minus P3 whatever you have computed. So, you will get your d square 3 d square delta 3 upon dt d square delta 3 dt square is equal to 180f upon 9 into 1.9439 minus 5.531 sin delta 3 minus 0.755 degree, right. And thank you very much, we will be back again.